Okay, have a look at page 1 of your worksheet. Okay, we just do some question before we take a short break. Now, what is the reasonable estimate of the average gravitational force acting on a fully grown woman standing on the earth? Okay, now this one is something like your estimation questions. So what is the possible value? You know that weight is mg. M is actually W over G. Okay, so right now, to make your life a lot easier, let's just assume G is 10 meter per second square. You just want to get roughly the value of the mass. What are the value of the masses corresponding to all these weights? 60 divided by 10 gives you 6 kg. 250 divided by 10 gives you 25 kg. 350 divided by 10 gives you 35 kg. 650 divided by 10 gives you 65 kg. Now, logic will tell you which one. If you remember your own weight, and then you compare your weight with the weight of a fully grown woman, the answer should be D, isn't it? I don't think you weigh 6 kg. You definitely do not weigh 25 kg. 35 kg, maybe for a girl, yes, but 35 kg is very light. Most of you guys will hover around 50 kg and so, right? The weight of a fully grown woman should be around here. This is a more reasonable estimate. So the answer is D. Okay, this is an estimation question. But you have to make an educated guess of what is your mass first, and then compare it with your own mass. Any mass that is lesser than your own is definitely out already. Okay, right, so answer for this one is D. Then you move to question number 11. Okay, question number 11 says that you have a molecule of mass m traveling at speed v that hits a wall in a perpendicular direction, and the collision is elastic. Okay, when you read your questions, try to identify keywords. Okay, for paper 1 especially, because the nature of paper 1 is such that it's normally tricky, you have to train yourself to start looking out for keywords. This one, they tell you the collision is elastic. Okay, what will be the changes in momentum and kinetic energy of the molecule caused by the collision itself? So let's try to visualize what's happening here. Let me clear off the diagram. You want elastic collision. You have a wall, and then you have an object that hits the wall. Okay. It is an object with mass m that hits the wall with speed v. Okay. And then after that, by right, it should also rebound. Okay. It should actually rebound with speed v too, because of this thing here. They tell you the collision is elastic. When they tell you the collision is elastic, the speed at which it hits will also be the speed at which it rebounds. It's actually from this relation, relative speed of approach equals to relative speed of separation. Okay, this was one of the criteria for elastic collision, where we say relative speed of approach equals to relative speed of separation. Over here, your relative speed of approach is actually v minus 0, giving you just v. Okay, so by right, after the collision, the relative speed of separation should also be v. Now the wall itself is always going to be 0 meter per second. The wall won't move. Okay, so the only way you still have relative speed of separation equals to v is if this one moves with v itself. Okay, that's the understanding behind that. But in general, you can just think of it as this way. If you have a stationary object and one object hits the stationary object and they tell you the collision is elastic, the speed before and after is definitely going to be the same. Okay, So the first key takeout point here is that due to elastic collision, speed at rebound is also v. Okay. Now they want change in momentum of the object. This one. What will be the change in momentum? So earlier in the notes, in the first page, I told you you want to find change in momentum. I mentioned to you it won't matter whether you take the final momentum minus initial or the initial minus the final. It doesn't matter which one you take. But just make sure that you always have a proper sign convention defined. So right now I can say that I want to find the change in momentum. Maybe I just take the initial minus the final, and I say that my sign convention is rightwards positive. This one will actually be just mv minus with negative mv, giving me 2 mv. So your choices or answer is anything with 2 mv. Okay, your change in momentum is not going to be 0. It's not going to be mv squared. It's actually just going to be this one. Okay, this one is 2 mv. This is the only answer choice. Your answer is actually going to be C. But let's go one step further and identify whether the change in kinetic energy is correct. When you want to find out the change in kinetic energy of the object, okay, bear in mind this is the change in kinetic energy of the object, the molecule in this case. What is the change in kinetic energy? The change in kinetic energy is your initial Ke minus final Ke, or final minus initial, or whichever it is now. This one you can say is actually half mv square minus half mv square is actually going to be 0. So this is actually consistent with what you see here. Okay, it's 2 mv and it's 0. So your answer is C. Okay, so this part should be okay. The next question, we've done this already, so this one I'll just skip. And then 13, I mentioned that you can just do it as your homework. So I'll go through this with you also. Okay, so this question here, you can do it 2 ways. The long-winded tedious method or the shortcut method. The shortcut method is the ones that I taught you last that time, where you consider this entire thing as a single body. Okay, so I'll go through both methods for you. Now, if I go through the first method as separate bodies, this one I'll just go through it very quickly with you. You consider them as separate bodies. What are the forces acting on both those objects? A box of mass 8 kg rests on a horizontal rough surface. A string attached to the box passes over a smooth pulley and supports a 2 kg mass at the other end. When the box is released, a frictional force of 6 Newton acts on it. What's the acceleration of the box? Okay, so whatever acceleration you have here will also be the same as the acceleration that you have here. Okay, if you consider the forces acting on the individual objects, this one would have a weight of 2 times 9.81, and then you have a tension T. This one you also have a tension T, okay, and then you now have a frictional force of 6.0 Newton. Now, no doubt you can also say that there's a weight of 8.0 times 9.81 and a normal reaction force here. But you see your acceleration and if you compare the direction of your acceleration with the direction of these two forces, they're perpendicular to each other. They would have nothing to do with A. So this one I normally will not consider. Okay, it will be correct to say that there's a weight there and the normal reaction force there, but it doesn't contribute anything to the acceleration that I'm interested in. So I don't really bother about the forces. The only forces that will contribute to the A is these two. Okay, so based on what you have here, you try to work out the free body diagram. You already work out the free body diagram. You now try to work out the acceleration by considering both objects. If you use fnet equals to ma, the first object would be t minus 6 equals to 8a. Then you consider the second object, it will be 2 times 9.81 minus t equals to 2a. This is the second one. Okay, this one, if you want to, this one is for this. And then this one is for this. So recall that I mentioned to you, when you want to determine whether the forces are positive or negative, you just look at it with respect to your direction of acceleration. Any force same direction as your acceleration will be positive. Any force opposite in direction to your acceleration will be negative. Okay, so that's how you determine that. Now from here, you can actually just do this. You just say equation 1 plus equation 2, because you see this is t, this is negative t. You add both up, you're going to cancel off. So you're just going to get 2 times 9.81 minus 6 equals to 8a plus 2a. Your final answer should be 2 times 9.81 minus 6 divided by 10. You're going to get 1.362 meter per second squared, which is answer A lah, if you round up to SF. Okay, so this one is the first method if you consider as a separate body. This one if you consider as a single system. You consider as a single system, that time I mentioned to you, you imagine laying these objects flat. Okay, if you try to imagine laying them flat, it could be 8 kg like this, and then it could be 2 kg like this. In general, they're moving like this, with acceleration towards the right like this. Your forces acting would be 2 times 9.81, and then your 6 Newton here. Okay, your tension T you do not consider because they cancel each other off. So these are the only forces that you can identify as acting on the system. So now if you apply F net equals to MA, it will be 2 times 9.81 minus 6 equals to A plus 2A. A would just be 1.362 meter per second square again. Same like your previous method. Okay, this and this, same answer. Okay, so it really depends on you, which are you more familiar with. Okay, now what is the definition of force on the body? This one I mentioned to you, it is rate of change of momentum of the body. So this one, we skip that. Let's go to the next question, June 15, P12. All right. Okay, now a firework rocket is fired vertically outwards. The fuel burns and produces a constant upward force on the rocket. After 5 seconds, there's no fuel left. Air resistance here is negligible. What is the acceleration before and after 5 seconds? Before and after 5 seconds. So rocket fired vertically outwards, fuel burns, produces a constant upward force on the rocket. After 5 seconds, no fuel left. And air resistance is negligible. What is the acceleration before and after 5 seconds? This one, you can just try and visualize this. Say before the 5-second mark, you have your rocket. Okay. And then after your 5-second mark, you also have your rocket. Now, let's consider some of the forces that are acting on your rocket. Before the 5-second mark, you have the weight, and then you have a constant upward force on the rocket. Take note of the word constant. Okay, so this constant outward force F is constant. Okay, and then another thing for you to note here is this: after the 5-second mark, there's no more fuel left. That means the force F here is no longer present after 5 seconds, isn't it? Because the fuel has been burned off. So you would expect to still have the weight. Okay. Now, before we go any further, there is a reason why they mention specifically about the fuel. Okay. They tell you the fuel burns and produces a constant outward force on the rocket. After 5 seconds, there's no fuel left. So from here, you can infer that during burning of fuel, mass decreases. Okay, maybe I better rewrite this properly for you. This one is during burning of fuel, mass decreases. Therefore, weight decreases. Okay, because you're burning off your fuel, your mass will decrease. So that in turn causes the weight of your rocket to decrease. So this one here, you can say that before the 5-second mark, this weight is actually decreasing. It is not constant. Okay. Now, after the 5-second mark, there's no fuel left. What can you say about this statement here? When you have no fuel left to burn, the weight remains constant. So this one would remain constant. Okay. This is fact number 1. During burning of fuel, mass decreases, therefore weight decreases. So this one is fact number 2. No fuel left to burn, weight remains constant. So visualizing it, this is what you get. So what you want to do now is you want to apply F net equals to ma to describe the acceleration. Now when you apply F net equals to ma for this one, say your acceleration is upwards, say your acceleration is also upwards. Your net force here is going to be F minus W equals to ma. Or maybe I don't write it like this. Maybe I just write it as F net equals to F minus W. Okay. Now before the 10-second mark, before the 5-second mark, this one remains constant, but this one is decreasing. Your weight is decreasing. If your F net is actually the force F minus of the weight, F being constant here, W is decreasing here. What can you say about the F net? Is F net gradually increasing with time or gradually decreasing? Bear in mind that you're minusing off an even smaller value now. I could give you maybe 10 minus 5, 10 minus 4, 10 minus 3, 10 minus 2. So what can you see about the resultant value here? This one will be 5, this one will be 6, this one will be 7, this one will be 8, isn't it? So because you're minusing off a value that is decreasing of a constant value, your F net is actually increasing. So your acceleration would therefore increase. Okay. Right. This one, how would I explain? This one, I will say that because a decreasing value of W is subtracted from a constant value of F, the F net increases, okay? Because you have a decreasing value of W that is being subtracted from constant value of F, your F net will increase. Therefore, your acceleration increase. So it will be correct to say that before the 5-second mark, your acceleration should be increasing, okay? But how about after the 5-second mark? After the 5-second mark, you no longer have any rocket fuel burning, you no longer have any F, you no longer have your weight decreasing also. So over here, your F net is just going to be your weight. Okay, so over here, your W is constant, F net is constant, therefore A constant. So it cannot be 0, it must be constant. Answer is C. This is for this one. This is June 15 P12, answer choice C. Okay, so June 15 P12, let me just double check the answer with you. Yeah, answer is C. Okay, right, so that part is fine. Okay, then you should move on to the next question. Trolley X moving along a horizontal frictionless track collides with a stationary trolley Y. The two trolleys become attached and move off together. Which statement about this interaction would be correct? Okay, so let me just clear off the stuff here. Right, so if you look at the questions here, move along a horizontal frictionless track. If this is horizontal frictionless track, this one is already telling you no external force. Therefore, it's a closed system. Okay. So it collides with a stationary trolley Y. The two trolleys become attached and then move off together. Now, this statement here already tells you that if they move off together, they must be perfectly inelastic. Whenever you see objects move off together after collision, this is already perfectly inelastic. Okay. So which statement about this interaction is going to be correct? Now, if you read the question, the statement one by one, start the KE or trolley X is changed to momentum in the collision. These are two different quantities. They are not related. Momentum and energy are two different physical quantities. They are not related to each other. So this one is out. Momentum of trolley X is changed to kinetic energy in the collision. This is also out because it's talking about one quantity changing to another different quantity. Okay. Now, trolley X loses some of its momentum as heat. Again, this is telling you momentum change to energy. This is out. Okay. Now, trolley X shares its momentum with trolley Y, but some of the kinetic energy is lost. This one is a more sensible answer. You can think of it as trolley X moving like this, hitting trolley Y. This is the before collision case. Then after the collision case, it will be X and then Y moving with a certain speed V. Okay. So this one, it was stationary 0 Newton per second. Then this one, I could give you maybe it's moving with a momentum of 10 Newton second. Your sum of initial momentum is 10 Newton second. After the collision, because this is a external, it's a closed system, it's an isolated system, so your final momentum will also be 10 Newton per second because the momentum must be conservation of momentum. Okay, so but the thing here could be that your momentum, I told you earlier just now that the momentum of the system will not change, but the momentum of the objects inside the system may change. So it could be that although you say that this is 10 Newton per second, this momentum, after it collides, the momentum of object X after it collides with Y is such that some of the momentum of X has gone on to Y, has been shared with Y. It could be that maybe X is now 6 Newton per second, and then Y is 4 Newton per second. If you add both of these up, you're still going to get 10. But right now, the momentum of the objects are different. From 10 Newton per second for X, it became 6 Newton per second. For 0 Newton per second for Y, it became 4 Newton per second. So it will be correct to say something like this. Trolley X shares its momentum with trolley Y, but some of the kinetic energy is lost. Okay, so this part here will be more for this part. Now, the part where we say that kinetic energy is lost is because this is a perfectly inelastic collision. Okay, just now I wrote, yeah, maybe I use this one. Just now I told you that because this one, they move off together, they are perfectly inelastic. Therefore, Ke is not conserved. Therefore, total Ke is not conserved. Okay, this one will be for this one. Some of the kinetic energy is not. Just now I mentioned to you, total Ke is only for perfectly elastic or elastic collision. Any other kinetic energy is not conserved. You would have some losses. Okay. Right. So that one, the answer is D. So this one should be fine. Okay. Then we move on to question number 12. Now, which an astronaut throws a stone with horizontal velocity near the moon's surface. Which law describes the horizontal and vertical forces acting on the stone after release? Right, this is a bit related to what you learned in kinematics previously. If you have an object, okay, now maybe I don't draw the table or the cliff here. If you have an object, a stone that you throw with a horizontal velocity v x here near the moon surface, how will you describe the horizontal and vertical forces acting on the stone after the release? Now, because this is near the moon surface, there's no air, therefore no air resistance. This is one keyword here. Okay. Then horizontal velocity was this one. Okay, they want the horizontal and vertical forces. Now, when they project the object with a horizontal velocity, horizontally, there's no forces, right? You have 0 horizontal force. But what about vertical forces? Now, you are having your stone being projected near the moon surface. The moon has gravitational pull. Okay, the moon has gravitational field. Okay, the moon has gravitational field. Therefore, stone will have weight. Okay, so the moon will exert a gravitational pull onto the stone, which you know as the weight. Okay, so this one, when you're talking about the vertical force, you actually have constant vertical force, i.e. the weight. Okay, so your answer would be C. Okay, no air resistance here, so you don't need to consider anything. No air resistance here, you can say that, oh, horizontally, there's definitely not going to be any forces. All right, and then after that, for vertical part, since there's no air resistance, the vertical forces won't change either. It's only just the weight. The weight won't change. Okay, so answer for this is C. All right. So zero horizontal force, constant vertical force. All right, then the last one is question 13. Newton's third law of motion is often summarized as every action force has an equal opposite reaction. A book rests on a table. If the weight of the book is the action force, what is the reaction force? This is the one example that I explained last week. Okay, so we'll just go through this again. Right, so if I try to draw for you something, this is your book, this is your earth, this is the book. Okay, the earth will exert a gravitational pull on the book, which is your weight. Okay, since the earth exerts a force on the book known as your weight, the book will also exert a force back onto the earth with a magnitude equals to your weight. Okay, this is your Newton's third law. Equal forces, equal opposite forces, same type of force acting on opposite bodies. Okay, this one. So if they tell you right now the book rests on the table, if the weight of the book is the action force, what is the reaction force? This one they're actually asking you for the weight. All right, so this one is how I started explaining it to you that day. So without anything in between the book and the earth, you will understand the book will actually fall down towards the earth, towards the ground. But what if somehow along the way, you put a table in the path of the book? Okay. Now you put a table in the path of the book, like this. The book will still have the weight due to the earth. The earth will still have W due to the book. Okay, this is the equal opposite pair. But the thing now is that because you have a table here, all right. Now you see, if I tell you you have a table, you push down on the table with a force of F, the table will push back out on you with a force of F, right? Correct? Then right now, your book with weight W, because the table is in the way, it wants to fall down to the ground towards the earth, but your table is in the way right now. So what will happen is that the book will actually push down onto the table with a force equals to W. Okay, maybe I just write this one here. It will push down with a contact force equals to W. Okay, so the book is exerting a contact force on the table which is equivalent to its weight, but the table will in return exert an equal opposite force back on the book according to Newton's third law. So you also have another equal opposite contact force here. This is equals to your weight, but you know it as your normal reaction force. So right now, when you're talking about the action-reaction pair, this is action-reaction pair. This is the action-reaction pair. This one is for the contact force between book and table. This one is gravitational force between book and earth. Okay. So right now they are asking you the weight of the book is the action force. What is the reaction force? They're specifically singling out this weight. The weight of the book is actually the action force. What is thus the reaction force according to Newton's third law? The reaction force is actually this one. It is going to be the pull of the book on the earth. Okay. All right. When you see the wording, the weight of the book here is the action force, this is actually already referring to the gravitational force of earth on book. Okay, so you need to relay back to the other opposing object and the same type of force. Okay, the push of the book on the table, the push of the table on the book, this one is actually talking about the contact forces, not gravitational forces. This one I won't consider. Okay, the pull of the earth on the boat, this one is actually the weight itself. It's actually this one itself. So it makes no sense to put this. The only one to make sense is 8. Okay, so this one, number 13 is 8. All right. Yeah, it takes some time to get used to this. But this question does come out occasionally. It's something they like to ask. Okay. Then another thing I would add is this now. If you were to just single out the free body diagram of the book itself, it would have your weight, it would have your normal reaction force, but this one is your gravitational force. This one is your contact force. Okay, these are not the action reaction pair. This and this are not the action reaction pair. The action reaction pair belongs to something else. Okay, right, so that part is okay. Then we go on to the next one. Okay, which of the following statement is the principle of conservation of momentum? Just now we learned this already. Now, momentum is the product of mass times velocity. This one, although the statement is correct, this is the definition of momentum. So it's not something you want. In an elastic collision, momentum is constant. This one is only partly true. Momentum is constant for all collisions in an isolated system. Okay. This one is only telling you part of the story. It's part of this is actually I think this one is better to write it as the effect of conservation of momentum. Is because of conservation of momentum that you can say that momentum is constant for elastic collision, but this is not the principle of conservation of momentum itself. The principle of conservation of momentum is this. The momentum of an isolated system is constant. Okay, recall just now that I mentioned to you, if momentum is conserved, the momentum of the system would remain constant. It will not change. Whatever momentum you have before collision is going to be the same as the momentum after collision. I think I wrote it somewhere around this page just now earlier when I explained to you. So momentum before and after always will be the same under conservation of momentum. That means it's constant, no change, right? So the idea was sum of initial momentum equals to sum of final momentum. If originally I have if originally I had 10 Newton per second, this one should be 10 Newton per second. This one is conservation of momentum. You have no change in momentum. It remains constant. Okay. Force acting on a body is proportional to rate of change of momentum. This is definitely wrong. This is definition of force. Definition of force, not conservation of momentum. So 10 is C. All right. So this one is okay. Okay, then we go on to the other one. You have an object that strikes a stationary object. Okay. Right, so this one, let me just clear off the thing. Now you have a moving object that strikes a stationary object. The collision is inelastic. The objects move off together. Which row shows possible values of the total momentum and total Ke of the system before and after the collision? Okay, so what are the few keywords here that you can see? Collision is inelastic. They move off together. All right. Now, the moment you see this one here, you can already see, you can already say that total Ke is not conserve. Because total K conserve only belongs to elastic collision. So the moment you see the wording in elastic, okay, number one, total K is not going to be conserved. Okay. Then after that, you see no mention of any external forces, right? So you can assume that it's closed system or isolated system, therefore conservation of momentum applies. Okay. You don't see any mention of friction, air resistance, or any other forces acting, right? So you can assume it's a closed system, therefore conservation of momentum applies. Sum of momentum before collision is equals to sum of momentum after collision. All right. So then you can try to evaluate from here. You see answer choice A. Let me use a different color. Total momentum before collision is 6. After collision is 2. This one is conservation of momentum not satisfied. So answer choice A is definitely wrong already. Okay, but then you see answer choice B, C, D, they have the same momentum before collision and after collision. So this one, conservation of momentum, is obeyed. All right. So this one already satisfy this criteria here. But then after that, you look at the kinetic energy criteria, you know that kinetic energy is not conserved. It cannot be the same before and after collision. If anything, the energy must always be less, okay? The one thing I can probably say is that total final KE is always less than initial total KE because energy is converted into other forms. Okay, your total final K will always be less than the initial total K because the energy is converted into other forms. All right, so not only will the total K not be the same, it should be less. So like this one here, you see this one is saying that the KE is conserved. This is out. All right. Then after that, you see the other, this one is already out. Let me just highlight the ones that are out. This one is out. This one is out. Okay, so that means only B and C. So which one is a more sensible approach? This one is saying that 30 kilojoules, sorry, this is the total K is 30 before collision, then suddenly after collision, it becomes 90. You suddenly gain energy after collision. This one is definitely out. But then if you look at the last choice of answer, total initial K is 90. Total final K is 30. This one you have energy loss. It is consistent with what you see here. So this one is correct. Answer is C. Okay. So there's a logic here that you need to somehow follow. Okay, that's why it's important to know the criteria. If you don't remember the criteria, it's a bit difficult to do questions like this. All right, so answer choice is C. Okay, this one. You see that conservation of momentum is obeyed, then you have loss in KE. KE is not conserved, and there's loss in KE. Okay, in other words, there's loss in KE. Maybe I just write this here. This one I can probably write it is IE. There is loss in KE. Okay, so that part should be okay, right? So this part is okay. Then we move on to the next one. Okay, now look at the next page. Two balls X and Y are moving towards each other with speeds of 5 meters per second and 50 meters per second respectively. They make a perfectly elastic head-on collision and ball Y moves to the right with a speed of 7 meters per second. what is the speed on and direction of ball X after the collision? Okay. So based on what you have here, you can see there's a keyword again. Perfectly elastic. Okay. They say it's an elastic collision. Okay, so elastic collision, KE total, observe. Every time you see the word elastic, just know that these two terms will always come up. KE total, conserve, and then relative speed of approach equals to relative speed of separation. Okay, that is what you want. All right. Now, what is the speed and direction of ball X after collision? They've already given you the case before collision, and they're kind enough to tell you what is the direction and speed of one of the balls after collision. They say the ball Y moves to the right with a speed of 7 meters per second. So ball Y moves towards the right with a speed of 7 meters per second. However, ball X, nobody knows whether is it going to be moving towards this side or towards this side. You just do not know. All right. Now you may notice that there's some similarity with this example, with the example I did for your notes. That time we found out what is the velocity of sphere X or the object X, isn't it? But note that one was found using conservation of momentum. All right. What I'm talking about is this example here in your notes, page 10. We had something similar. Something collides head on like this, and then after that one of it moves off, and then we ask you to find what's the velocity of trolley X. That one, the way we solve it was by using conservation of momentum. Now, if you are trying to do the same thing here, you cannot use this because there's one big issue here. Conservation of momentum cannot be used because, yeah, you know the speed, but you have an issue of not knowing the mass right now. You don't know what's X, you don't know what's Y, so you actually have two other unknowns. You cannot solve anything here. All right, so conservation of momentum cannot be used because the masses are unknown. So this one you cannot use. So in case you're wondering why sometimes I can use conservation of momentum, why sometimes I do use something else. In this case, you cannot use conservation of momentum because you don't even know the mass. You'll be stuck. All right. The only way you can use this if they tell you two identical balls X and Y are moving towards each other. Then if they tell you it's two identical objects, then you know it's the same mass. After which they will cancel off. But now because they didn't say anything, you don't assume that. All right. So you cannot use this one. You have to use the criteria that is specific to elastic collision. So the easiest one is to use relative speed or approach equals to relative speed of separation. Okay. So let's just go with this. If I were to ask you this one, maybe I better draw it. Oh, yeah. This one here, what is the relative speed of approach? This one, the relative speed of approach is going to be, notice that they're both moving towards each other. So this one, you just add up the speeds. Okay. This one will be 5 plus 15, giving you 20 meters per second. All right. So if the relative speed of approach is 20 meters per second, the relative speed of separation should also be 20 meters per second. Okay. So right now what you do is that you evaluate each of these choices, which of these will give you a relative speed of separation of 20 meters per second. So to make your life easier, you can just draw something like this. Okay, if X is moving, maybe I use a separate color. Okay, I use blue, so it's easier for you to see. Okay, what is the relative speed of separation here? If you're talking about A, X is moving 3 meter per second, Y is moving 7 meter per second. Opposite directions, isn't it? So you add up the speed. This one will be 3 plus 7 equals to 10 meter per second. Okay, but how about for B? B will be 13 meter per second. Y would be 7 meter per second. Again, they're moving in opposite directions, so you just add them up. This one is 13 plus 7, giving you 20 meter per second. Now notice that this is the same as this now. So by right, B should be the answer. But if let's say you want to continue evaluating for C and D, you can also, just to prove a point. If 3 is going, if C is 3 meter per second to the right, Y is 7 meter per second towards the right. They are both moving in the same direction. You just take the higher speed minus the lower speed. So it's 7 minus 3, giving you 4 meter per second. And then after that, you choose answer choice D, 13 meter per second, 7 meter per second. Again, they're both moving in the same direction. Just take the higher speed minus the lower speed. 13 minus 7 will give you 6 meter per second. So you see, none of them have the same relative speed of separation as approach other than B itself. So answer choice is B. Okay, so this is how you use relative speed of separation as well as relative speed of approach. Okay, so that part is fine. Then after that, we move to something else, another separate question. Okay, this one is, it actually takes into account kinematics also from another separate chapter from your previous chapter, but we can still do this also. Okay, now you have a wooden block that is freely supported on brackets at a height of 4 meter above the ground. Okay, 4 meter. The bullet of mass 5 grams is shot vertically upwards into the wooden block of mass 95 grams. It embeds itself inside the block. The impact causes the block to rise above its supporting brackets. The bullet hits the block with a velocity of 200 meters per second. How far above the ground would the block be at the maximum height of its path? Now this is a case before collision. After collision, you would expect the block here to already have the bullet embedded inside, and you will move off with a velocity v. Okay, this is the after case now. All right. So what you're interested to know now is this velocity first. Okay, you actually have two objects, the bullet and the wooden block, before the collision. Now after collision, both bullet and the block are one single object. So the first thing you want to know is actually the velocity with which the block starts to fly out. Okay, this one you can just use conservation of momentum. When you say this conservation of momentum is actually going to be the momentum of the bullet, which is 0.005. Sorry, let me just use a color that is easier to see. 5 grams divided by 1,000 to give you kg 0.005, right? Then multiply with the speed is 200 meters per second. Then the block itself is stationary, so it's just 0. Okay. After collision, you're gonna have the mass of both block added together, both objects added together. 5 grams of the bullet and 95 grams of the block. this is going to give you 0.005 plus 0.095 times with V, right? V you see is going to give you something else. I think it's 10 meter per second. Okay, you're going to get 10 meter per second. All right. So your velocity here is going to be at 10 meter per second. So the question wants you to find out how far above the ground will the block be at the maximum height of its path. When the bullet hits the block and embeds itself inside, this block will start to move with a velocity of 10 meters per second. It will go up and then reach the maximum height before it falls down. So the question is asking you, how far above the ground will the block be at the maximum height above how far above the ground will the block be at the maximum height of its path? So what they want is this one. This is the height they want. Okay. Now you need to find out what is this one in the first place. Okay. You can actually use your kinematics here. There are two ways to go about this. This one is either you use kinematics. Remember in kinematics, if let's just say you have an object that's moving at 10 meters per second, and then you want to find out the distance move to maximum height, you can use kinematics. Right, let me just erase this. You can treat this something like a kinematic question, where you have an object with an initial speed of 10 meters per second. Then once it reaches maximum height, the V is 0. So you want to find out the S here. You can just use V square equals to U square plus 2AS from your kinematics, which gives you 0, 10 square plus 2 negative 9.81 times S. Because your initial direction of motion is upwards, upwards is positive. That's the reason why your G is negative here, because G is downwards. So your S is going to be 10 square divided by 2 divided by 9.81. You're going to get an answer of 5.1 meter. Okay, this is your height move from the initial point. Now, then you may be tempted to write this as the answer. This is wrong, because the question wants how far above the ground. Okay, this 5.1 here is actually this 5.1 measured from here to here. This one here being your max height. Okay, this is your 5.1. When the question wants the height above the ground, you have to add an additional 4 meter. So your H that you want is actually supposed to be 5.1 plus with 4, giving you 9.1 meter. The answer is going to be C. Okay, so notice that there's actually one question that requires your knowledge of two different chapters, dynamics and kinematics, right? So this is just one way of doing the same question. There's also another method to do this. This one is just by using conservation of energy. If you want to use conservation of energy to do this, you can just think of it as this. As your object moves up, your GPE will be increasing, right? And then your KE will be dropping. You have increase in GPE because your height increases. You have drop in KE because you're slowing down to a stop at maximum height. So the general thing you would know is that your changes in GPE equals to the changes in your KE. So you can actually just write this as this: change in GPE, change in KE. So you have mg delta h half mv squared minus 0. The 0 comes from your this part here, which was 0 meter per second. So eventually you see that you can simplify this. The methods will cancel off, giving you delta H as V square over 2G. So it's 10 squared divided by 2 times 9.81, which will actually give you back 5.1 meter. Okay. So you see this 5.1 meter that you find is actually going to be the same as this. All right. So from here, you just add it back up to 4 meter, you're going to get back the same answer as 9.1 meter. All right.